share yours. So Andrew will speak about the design and application of TADF emitters for blue and white OLEDs.
Okay, can everyone see that?
Yes.
And when I click it?
Yes, all good, all good.
All right, excellent. All right, well, so thank you everybody for having me here. Thank you, Bronson, for organizing these, which have been really quite good. As you mentioned, I'm going to be talking about kind of the opposite side of the coin when it comes to optical stuff and applications, rather than looking at photovoltaics, instead looking at OLEDs, which do exactly the opposite. Oh yeah, we're good. All right, so as Kyra kindly sort of introduced, when we're looking at the interactions of light and matter for organic electronics, we're usually only thinking really about either singlet states or triplet states. There are other things that can exist, but usually they're not that applicable. The key difference between the singlet and the triplet states, though, is that whereas the singlet states can emit relatively quickly and efficiently, the triplet states, because of the unpaired electrons in the HOMO and LUMO, that transition is strictly forbidden, but it can in reality happen in a lot of circumstances. As a result, you do get these two different channels of emission from different organic emitters, fluorescence from the singlet state and phosphorescence from the triplet state, which is much longer lived and usually of lower energy as well. So I've been very ambitious. I've tried to embed a video that can show this. Hopefully you guys can see it. In this video, we've got a laser point hitting a material that undergoes both fluorescence and phosphorescence. And in the clear parts where it's not protected from oxygen, the triplet states get quenched relatively quickly, and we only see the higher energy blue emission. Whereas with the aluminium backing, you also get the triplet emission of phosphorescence, and you can actually see how long it really lives. To get lifetimes, on the order that you can observe them with unaided sight is pretty interesting when you think about it for purely electronic transitions. All right. So my background actually does come from solar cell point of view. I did a PhD looking at triplet annihilation upconversion, where we use the long-lived property of those triplets as a way of pooling energy so that we can take low energy photons that would otherwise transmit through a solar cell, sort of build up a population of triplets, which can then undergo a bimolecular process to be pumped back up to their singlet state and emit at a higher energy than what you're originally absorbing. The useful thing about that is that you can get those low energy photons converted up to a higher energy than the band gap of your solar cell would otherwise be, and then they become useful again for whatever that solar cell is. At the end of my PhD, though, I accepted a job at Durham University, which is a lovely place, and it's been really good there. Right now, I'm actually on holidays since March for 1 month, waiting for flights and things like that to sort themselves out so I can get back. But the labs are shut currently, so there hasn't been a very strong rush. What they do at Durham, though, is related to that PhD work, but again, kind of in the opposite sense. So whereas for solar cells, we can use triplet states as a way to augment things, in LEDs, triplets are a scourge that have to be managed if we're going to get decent efficiencies at all. The reason for that is that when you excite in an LED, you're injecting uncorrelated holes and electrons, and just by the random combination of either spin up or spin down, you're going to be generating in only 1/4 of the time emissive singlet states, whereas 3/4 of the time you're going to get triplet states, which for normal fluorescent materials just really don't emit on a time scale that's suitable for LEDs. What this means is that the earliest LEDs, the ones that relied on fluorescent dopants in some other kind of host, were really capped in terms of what sorts of efficiencies they could reach. If only 1 out of 4 charge recombination events gives you emission, when you then factor in the difficulty of getting light out of the LED itself, really 5% is about the maximum you can hope for in one of these first generation fluorescent LEDs. Now, what people pretty quickly figured out after that was that you can actually use phosphorescent materials which emit from the triplet state. Usually these are sort of cyclometallated uridium or platinum materials, where the heavy atom in the center of your complex can give you strong intersystem crossing. So all of your singlets get converted into triplets, so you don't have to worry about balancing 2 different states. but it also means that the otherwise forbidden transition from the triplet state to the singlet state becomes allowed enough that you can actually make very good LEDs out of phosphorescent dopants. The trouble with the phosphorescent LEDs, though, is that if you look in this middle picture, the singlet state is higher than the triplet state, and we're emitting out of the triplet state. So if we want a blue phosphorescent LED, that triplet state has to be high enough to give blue emission, which means that the singlet state is even higher still. And those really, really high accessible electronic states in molecular devices means that you start running it up into the barrier of sort of bond dissociation energy for the complexes that you're looking at. So it turns out that it's extremely hard to make good phosphorescent materials that are blue and have long lifetimes, because as you're injecting charges into them, you're populating singlet states. Those singlet states have a chance of breaking a bond somewhere, and so the LED dies pretty quickly as a result, just because of the energetics of the phosphorescent emitters themselves. So more recently, in the past sort of 10 years or so, this third generation of LEDs has sort of come into flavor, and that deals with these thermally activated delayed fluorescence materials. And it's interesting that that's the name that's been attributed, because it's not really the thermally activated nor the delayed fluorescence part of these TADF materials that's relevant for the OLEDs themselves. It's rather their ability to undergo both intersystem crossing from the singlet to the triplet state, but also crucially reverse intersystem crossing from the triplet back up to the singlet. And so what these TADF molecules do, you still get 25% singlets, 75% triplets, but those triplet states can be promoted back up to the singlet state, and everything emits out of there due to the reverse intersystem crossing. And because we're now emitting out of the singlet state again, some of those limitations in terms of getting blue emission in LED become a little bit easier to manage around, but these TADF materials have their own devils to deal with as well. Okay, so if I can click to the next slide. Yes, I can, good. So what ultimately determines the rate of this reverse intersystem crossing is whether or not the singlet and the triplet states themselves are close enough that thermal energy can pop one up to the other. So how do you get the singlet and the triplet energy close enough that they do it? Unfortunately, most conventional fluorescent fluorophores are just not going to work. So in this example of perylene, you can see that the HOMO and LUMO are strongly overlapping with each other. This means that there's a big exchange energy in the excited state electrons. And so the triplet state sits about half of the energy of the singlet state. And that gap is on the order of whole electron volts, which means that, again, for most normal fluorophores, TADF just doesn't happen because the singlet and triplet state really aren't anywhere near each other. So what do we have to do in order to arrange things so that newly developed molecules can have the singlet and triplet state close, and we can get this reverse intersystem crossing? This is a nice example here that kind of shows it. If you look at the HOMO and the LUMO of this acridine cyano joined donor acceptor molecule, you can see that the HOMO and the LUMO are actually very well separated, which means that the exchange energy there is small. And so the singlet and the triplet state will actually be relatively close together. But it also means that this excited state has a charge transfer character to it, which ultimately turns out to be the more relevant factor here. In this other recent paper, this kind of shows what those CT states can do that make them useful for TADF. In the picture here, this is all vials at the same concentration of this material too. So there's no tricks being played here. It is the same material, same concentration. But the difference is that going from left to right, we've got cyclohexane, toluene, chloroform, dichloromethane, and acetonitrile. So we're increasing polarity of the environment, and the color is shifting drastically. So we can change the singlet state of these charge transfer type emitters in order to tune it close to where what it turns out has to be a localized exciton triplet state is. And we can get that singlet and triplet energy to be close to each other by using external factors rather than having to sort of guess and get lucky through trial and error molecular design. Now, for different materials, using different donors or acceptors, those states can be in different places. They can be more tunable, like this material. They can be less tunable, like this material from the same piece of work. And sometimes that's a good thing, sometimes that's a bad thing. But ultimately, again, it's our ability to do that tuning that is really critical for getting TADF off the ground. In this, going back to this example, what you can then do with your sort of candidate TADF materials is have a look at their fluorescence in a particular environment, have a look at their phosphorescence in that particular environment, and calculate what the gap between the onsets of the singlet spectrum and the triplet spectrum are. In these two examples, the top one has a very small gap. You can see how the fluorescence and phosphorescence kind of lift off the baseline at about 400 nanometers for both of them. Whereas for the bottom one, there is a significantly larger gap. And as a result, when we look at the time-resolved photoluminescence of these materials, the bottom one with the bigger gap has a much slower delayed component, whereas the upper one with the smaller gap in blue is, well, it's got a faster component. And that speed of delayed component is what we can sort of access, is what we can use to access the size of the reverse intersystem crossing rate constant. All right, good. So no, I'll skip that. So what can you do then to get that number, that reverse intersystem crossing rate constant? Because it turns out that comparing singlet triplet gaps alone really doesn't cut it, because different materials have different sort of degrees of coupling between their different states. So in some early work that I did at Durham, what we did was say, all right, can we do some fancy fitting on the singlet time-resolved photoluminescence and extract the rate of reverse intersystem crossing directly from that? We had to make some approximations. The more complex, fuller picture of the TADF mechanism got turned just into, well, there's intersystem and reverse intersystem crossing and fluorescence. But comparing this to data from real materials, we found that the fitting, the black line for the singlet population, compared to the measured intensity of prompt and delayed fluorescence, it actually worked quite well. And you can see from this kind of data that we do have a prompt component of fluorescence, which occurs on lifetimes typical for what you'd expect for normal materials, but then also some other fluorescence, so same spectrum, but at much, much longer time. So that's the delayed part of TADF. Also, when you do these measurements at different temperatures, you find that at lower temperatures, where the T1 state might be below what thermal energy can provide to allow risk, the delayed component becomes slower and also smaller. So there's your thermally activated part of thermally activated delayed fluorescence. What was quite nice though from this work was that, improving upon previous methods, it was kind of an application of some of the tools that I picked up from the TTA research before, where sort of coupled differential equations are used quite commonly to get different rate constants out. And for the case of TADF, it meant that we had the ability to directly fit the singlet population and get out this parameter, the risk rate, which is really what we want for new and different TADF materials to be able to compare. What worked very nicely though, this was kind of in response to one of the reviewer comments, this approach of coupled differential equations also generates the triplet population, which we were able to match really nicely to some completely independent measurements of transient absorption of the same material. So we fit the fluorescence, we get these rate constants, we get a fitted triplet population, and that fitted triplet population actually lined up pretty well with the transient absorption, which had not been fit at all at that point. And the reason that these numbers obviously are important is that if you then go on to make an LED out of a particular TADF material, the maximum EQE that you can hope to get is really determined by mostly the PLQI, which is relatively straightforward to measure. But the degree to which that EQE drops off as you hit the LED harder and harder at higher brightnesses, that efficiency roll-off is really strongly controlled by the risk rate. So you want that risk rate to be high, you want that PLQI to be high, and if you've got both of those things, then you've definitely got a candidate good LED material on your hands when you're screening a bunch of different materials. All right, so to give you some examples of how you can then go about designing different and better blue TADF materials, in this first paper, we looked at an established material, number one, and some different structural analogs of it. Whereas in this one on the bottom, we looked at a single type of acceptor with some different donors attached to it that varied in their donor strength. And what we found was that compared to the starting material in that first work, if we changed it from para to meta connectivity, that's material one versus material two, it wrecked it. It made the efficiency much lower. It made the risk much slower. It also made the color less blue. So that was definitely not what you want to do, but of course, publication is all about showing not just what works, but also what to avoid. In contrast, if we add this methyl group to the acceptor, we found that that had some structural effects, which ultimately made it deeper blue, more efficient, fantastic. Some strange things going on with the roll-off and stability there, but ultimately that sort of just adds to the growing understanding of how to design these blue TADF materials. For that second paper I mentioned, what we found was that looking at just the fluorescence and phosphorescence, we could say immediately that this particular donor in the middle, the DTBU acridine dibenzothiazine, was the one with the smallest gap. So we made some LEDs out of that and got about 10%, which was spot on in terms of what the PLQI of that material indicated that it should be, and quite a nice deep blue color coordinate as well, which was dominated mostly by the strengths of the donor and acceptor segments. All right, some other work that's come out of Durham recently, which was really quite nice and exciting, is that it's not just molecular TADF materials that we can apply these approaches to. You can also make TADF using separate donor and acceptor molecules in what is called an exciplex. And although in an exciplex, you really don't get that level of structural control that you do with covalent bonds, what we were able to find out was that you can mix it together with a third thing that spaces out the donor and acceptor. And if you do that, you actually get significant increases in the PLQI, depending on what type of spacer you use, significant increases in the EQE of the LEDs that you make, and you also get a blue shift in the emission coordinate. So all fantastic things. That was kind of the highlight of 2019. And we then followed that up pretty soon afterwards, looking at some of the effects of using different donors, and found that you can kind of, not one-to-one, but the design rules are kind of starting to emerge on what kinds of exciplex donors work for this dilution strategy and which ones don't work as well. All right, so you might have noticed I'm using an interesting PowerPoint template featuring this Hyper OLED project, which is what I was originally hired on. Ultimately, this approach is kind of going beyond TADF, because what people have found in the last few years is that TADF materials, in order to have a good risk rate, that fundamentally limits some of the things about their fluorescence, which means that you can either get very, very good triplet harvesting, or you can get very, very good emission rate constants and color purity, but it's extremely difficult to engineer both of those things on a single material. What this hyperfluorescence approach, or TADF assisted fluorescence approach, hopes to achieve is to mix together a TADF material and another separate fluorescent material in the same LED. You get energy transfer from the TADF, which is doing the triplet harvesting, onto the fluorescent. And as a result, it's kind of a nice example of specialized roles, so to speak. In this kind of scenario, the TADF only really has to be good at harvesting triplets, and the fluorescence emitter only has to be good at fluorescing from its singlet state. And if you pick them correctly, what you can get is an LED that's got much nicer, sort of narrower emission, which is important for applications. You might get a situation where you can increase the overall rate of fluorescence as well, compared to the TADF material by itself. And you still get all the benefits of harvesting triplets from the TADF material, doing that kind of stuff in the background. We actually saw some results of this, I think, from the Cope group last week. But the trouble with these hyperfluorescent materials is that it is almost impossible to predict whether it's going to work well, or whether it's actually going to give you a performance hit compared to the TADF material by itself. In fact, although this Hyper OLED project was centrally concerned on hyperfluorescence and how to develop it, our main insights so far has been that it really hasn't been demonstrated consistently yet that you can get better performance in the hyperfluorescence than compared to the TADF material by itself. And this fee here from this citation is a good example of how you can kind of hide that result under the carpet. If you compare the TADF hyperfluorescence material in the blue dots compared to the fluorescent one by itself, yeah, you're getting a fantastic increase compared to fluorescent. But if you were to also look at the TADF material without the fluorescent, usually the maximum EQE that you can reach is still quite a bit higher. And we're sort of getting ready to publish our findings on these hyperfluorescent systems at the moment. All right, so that's all about blue LEDs, but this talk title had white as well. The reason I don't need to spend so much time talking about white, though, is that once you've got blue, that's most of the battle won. If you want to do a display, you then need also some other pixels that can produce green and red, but ultimately phosphorescent LEDs can kind of do that to a very, very good extent already. If you only need lighting, if you don't need arbitrary color, then the kind of shortcuts of human vision mean that you can just get away with a blue and not even as deep a blue as you would normally need, and an orange, and your brain will interpret that as a white as well. So once we've got good blue TADF materials, getting from blue to white is not nearly as challenging as just getting a good blue in the first place. Now, if you wanted to do that, though, there are some methods that are more complex, and there are other methods that are less complex. One of the more complicated ones, but ultimately the one that industry kind of wants to pursue, is mixing together different red, green, and orange, or red, green, and blue, or blue and orange TADF emitters together or in separate layers inside an LED. The issue with this, though, is that there's a huge amount of optimization that needs to happen before you can get a good white OLED based on co-evaporation of all the different components into the same emissive structure. So some work that I've put out recently with some collaborators that I'm quite proud of and trying to show off to you guys here is a different, much simpler, but still very successful approach, where we were able to take a working blue TADF OLED based on some of these emitters that I've already shown, put a polymer coating on top that had some parallenes embedded in it, and convert some of the blue into orange, such that the combination of the remaining blue and orange, or in later cases, blue, orange, and green, we're giving a really nice white color coordinate. But because we're not touching anything about the blue LED underneath, we were still getting the same kinds of efficiency and performance out of that OLED as we would have otherwise. So we didn't have to worry about very much optimization inside the LED. It was all external. All right, so to tell the story here, the situation was that Erkan was a visitor from Turkey who came for a sort of secondment during his PhD. And he brought with him some parylene dyes that he'd synthesized, but didn't really have a plan for what to do with them. One green one on the left side and an orange one on the right side. But what he and I quickly sort of noticed was that if you looked at the color coordinate of this blue TADF emitter, which is very, very well studied in our group, and the color coordinate of the photoluminescence of this orange parylene diimide, if you draw a line between them, you can actually find the white coordinate in between. And what that kind of inspired us to think was that, well, if we've got white in between these two materials, then surely some combination of the two is going to be able to give us a white LED. Luckily, the absorbance of the orange PDI didn't match up perfectly, but well enough with the blue electroluminescence of the TADF material. And so when we did this, it required some very sort of clever and slow and patient application of the blue of the orange down conversion layer to prevent the paralenes from aggregating. But when we did, we found that we actually got, a nice blue peak, a nice orange peak, and a white coordinate that didn't really go where we expected it to. It kind of went a little bit towards white, but as we got closer and closer, it curved away down into the sort of bluey purpley region. And at first we had no real idea of why that was happening. But then when we looked closer at the electroluminescence of the coated device, you can see that in red in the central panel of this figure, there's the nice Gaussian shape of the TADF by itself. But in the coated white LED, we've got these little dips at sort of 475 and maybe 530, which it turns out match up really nicely with the vibronic absorption peaks of the parylene dye itself. So what was going on was that the down conversion layer was actually also acting as a filter, and it was moving the blue coordinate of our starting position in CIE space further down the more of the parylene that we put on top of it. Now, this doesn't normally happen in LEDs where you mix things together inside the LED, because then there's either Foster or Dexter transfer, which quenches the energy donor's peak entirely rather than selectively. But we weren't doing that. We were just relying on emission and radiation and reabsorption by the parylene itself. But what we were able to do was apply some of the green parylene that he'd prepared as a sort of course correction through CIE space. And when we went on to characterize the LEDs themselves with these down conversion layers on top, either with an orange and green, or an orange, or just plain LED, or as well as comparing those, an LED with a plain layer of polymer on top to make sure that we weren't cheating and getting outcoupling enhancements. What we found is that we were able to get a very, very nice like 0.33, 0.33 color coordinate without dropping the efficiency of the blue LED by a noticeable amount. It's quite hard to compare these directly because once you test an LED, you've usually destroyed it as well. So we couldn't go back and apply this process to the same LED and compare exact with and without. But across the set of devices that we made for this, it looked like there wasn't really a substantial drop in efficiency compared to the blue LED underneath and the white LED that we constructed with the down converter layer on top. All right, so as I wait to go back to England, we've got some good news as well for some future work, recycling some ideas from my own PhD. I've recently been awarded some kind of startup funding to look at TTA in LEDs. So that's what I'm waiting to go back and pick up on. So thank you everybody for listening. There's a lot of collaborators that have contributed to this as well that are in the titles of those papers. Very much a group effort for many of these works. I hope you've enjoyed the talk and maybe learned something.
Thank you very much. Yeah, it's another interesting talk. So of course, we have maybe time for a very quick set of questions if there's some from the audience. So please, if anyone would like to ask a question, please jump in and do that right now.
David Huang here.
Hi, David.
Hi, Andrew. So I have a question about designing TADF materials. You talked about having to tune the singlet triplet gap, but do you also, the other factor is spin orbit coupling. So have you looked at strategies for enhancing spin orbit coupling?
I personally haven't, but I've kind of worked alongside in parallel some people who have in the group. Sort of if you put a sulfur in there, does that help compared to an oxygen? If you put a selenium, does that help? And generally the answer is not as much as you'd expect. So you can put heavy atoms in there and try and help spin orbit coupling that way, but it usually ends up being a small contribution compared to this vibronic coupling of singlet and triplet LE and CT states. Of course, it depends where you put it. Some people put bromine atoms all over their TADF and find that it works very fast, but you then have to start thinking about what's going to be compatible with inside an LED. Can you get away with adding all of these big heavy atoms, usually on the periphery of the molecule, without it falling apart?
Okay, thanks.
Can I ask a quick question?
Yeah, go ahead.
Great. Thanks. Thanks for the talk, Andrew. I just had a question about the, you had a slide where you showed the two different models for the TADF compounds. So one with the locally excited triplet state.
Can you still see what I'm seeing?
No, your
we
screen
can't see
is
your
not
slides.
shared.
No,
And then you had like a simplified model.
this one? Yeah.
That's the one.
Yep.
So my question is, when do we need, under what circumstances do you need to account for that locally excited triplet state? And when can you just sort of assume the simplified model that I think most people tend to go with anyway?
That simplified model, that T1 in the simplified model, is the locally excited triplet state, which comes from usually some fragment of the larger TADF molecule. There's a huge amount of like back and forth debate and history to this, but ultimately what people kind of started realizing soon was that the CT triplet it needs to kind of be there, but it's not the main event, because you don't get risk between the two CT states. So in that simplified model, that triplet state is the locally excited triplet state. It's usually something intrinsic to a particular fragment of the molecule. It doesn't really change with host environment, and you're moving the CT singlet to try and bring it into resonance with that local triplet. From an applications point of view, this simplified model works well enough that you can get risk rates out and compare a series of molecules and decide which ones you're going to make LEDs out and which ones you're not. If you want to use the full fat TADF mechanism, you need people smarter than me, because there's been some pretty hardcore theory papers on that stuff which I struggle to penetrate.
Okay, I mean, I suppose related to that, I mean, if the simplified model accounts for the data pretty well, why is the more complicated TADF mechanism then involving this CT state really needed?
From an applications point of view, you can kind of get away without it. The historical development of that, though, was that people were saying, we've got a CT triplet from phosphorescence, we've got our CT singlet, they're very close together, and yet this particular TADF material is not working, whereas some other one where they appeared to be further away was working. So in order to rationalize how some materials appeared to have low singlet triplet gaps but were kind of crappy, whereas other ones had much bigger gaps but were working very well, the key piece of understanding there that brought it all together was to recognize that sometimes you're not measuring the triplet state that's directly active. Like, it's still part of the process, but sometimes when you measure phosphorescence, you get the triplet energy of the auxiliary triplet rather than the one that's doing the coupling. And as a result, you get a singlet triplet gap that is not necessarily representative of the risk that you would measure otherwise.
Okay, thanks for clarifying that.
That's okay.
All right, we're a little bit over time. I think we will need to stop it there. Everyone, please join me in a virtual round of applause for Andrew. Very interesting talk.